Okay, so welcome to the 36th video in the Discrete Structures series, and we'll be resuming our discussion of recursive algorithms. In the previous video, we looked into the first four recursive algorithms, and they were exponentiation, factorial, GCD, and modular exponentiation. And we'll be continuing with the remaining three algorithms today, and they include the linear and binary search. And finally, we'll look into a recursive sorting algorithm called the merge sort algorithm. So let us get started with our search algorithms, linear and binary search. And before we dive into the formal algorithms, let's look into an example that's really intuitive and will help understand this concept. So let us consider that we have a dictionary. And I just mean the usual dictionary book with words and meanings. And the problem that we want to focus on is the task of finding a word in a dictionary. If we look into the process of finding any given word in an English dictionary, even though the dictionary has tens of thousands of words, we are able to find our words in a matter of minutes. So what is it about a dictionary that makes it so easy to find or search a word in it? And I think all of us agree that the reason is the dictionary being sorted. So if I let this line represent my dictionary, I know that the words appear alphabetically. So words that start with A lie somewhere over this range. If I'm looking for a word that starts with a Y, for example, I might be looking into this kind of range towards the end of the dictionary. So we kind of make an intuitive guess of where we might find a word. And even if I'm wrong, let's say I'm looking for a word that starts with a K, and I turn the dictionary on this page, on the middle somewhere. But I come to find that this page that I turn to only contains words that start with I. But even if I'm wrong, even if I didn't find my K, I know that my word is going to be the right of the dictionary. So anytime I turn into any given page, I'm basically splitting the dictionary into two halves. It might not be equal halves, but I'm basically splitting it into two sections. And no matter what word I'm looking for, I can entirely neglect one section and make sure that my word is in the remaining section. And this type of searching is faster because I didn't have to go through all of the previous words in order to find my word. In this case, in order to look for a word like kangaroo that starts with a K, the moment I turned my page into I immediately avoided the necessity to look at anything before I. But now imagine the same dictionary, but now the words are everywhere. It is not sorted and any word could be at any random position. Now if I need to find my word that starts with K, or any word for that matter, I have no other choice but to begin looking at the very first element and keep looking until my element is found. And this is what we are forced to do if the list is not sorted. So in summary, in order to search a list that is not sorted, I have to kind of move in a straight line. So my search is linear. Because see, I start just at the first element and move along this line until the last element is reached. But in case of a sorted list, I can immediately look into the middle element. And although it is extremely rare that this middle element is the word that I'm looking for, it is 100% guaranteed that half of the search space will be reduced. So looking back into my example, I was looking for a word with K. I hit I and I know that my word is in the right. I'll repeat the same process. I'll look in the middle and this time let's assume it's not K but Q. Okay, something after K. And what do I know now? See, this space I have already omitted. And finding Q has allowed me to omit this space as well. So I know that my word is now between this range only. And I can keep reducing the search space in half every time until I find my desired word or search item. So this type of search where we divide the space into two groups is called a binary search, bi for two. Okay, so binary search. And this will only apply if the list is sorted. And if the list is not sorted, a linear search would apply. So with that idea, let's get started with the algorithm. We'll first do linear search. The last thing that we want to do is forget that we are in the chapter of recursion. So in order to provide this recursive linear search algorithm, let us see how we can define this type of search recursively. So imagine that this whole thing is my list called A. The first element in my list is A1 and the last element is AN. And all the elements in are this list. And by our assumption, this list is not sorted. So we'll start looking at A1. And let me also tell you, the goal of the search is to return the position of the element. So let's say this list has 20 elements and the number 15 appears somewhere in that list. And let's say there are 10 numbers before 15. That means 15 will be my 11th number. So this position is what I want to return. And when we are talking in terms of A1, A2, A3, the 1, 2, 3 are the positions of those variables. So we'll be given an item X that we need to search. And we'll compare that X against each of A1, A2, A3 until one of them match. And whichever value matches, like for example, let's say X was 15. We don't want to return 15, but we want to return the position of that value 15. And let's say in this list 15 was the 11th element, we want to return 11. Hope that is clear. And now let's find the recursion. The first thing that we'll do is to compare x with my first element a1. Now if x matches the very first element, I can simply return its position 1. And if x does not match with the first element, I have to repeat the exact same process with the remainder of the list. So we started searching on a larger list from a1 to an, and if the item was not found, we reduced the problem to a problem of exactly same nature but a smaller size. So that is exactly what recursion requires. So we'll start the algorithm by writing procedure, and let us just call this search, and then it will take 3 arguments I, j and x. I'll tell you shortly why these are for, but let me mention that these are integers. And then we say that both I and j should be between 1 and n. Okay, so let's get introduced to these parameters. X, as you can see, is just the item that I'm searching for. So like this number 15 in the list that I'm looking for. And you have to understand that I'm actually searching a list called A. That list is not taken as an argument here. This is just given as a procedure for a search. If you are familiar to programming, you should assume that A is in some global scope. And it is A that has my n elements. So A is going to range from A1 to AN. And when I'm searching for anything in this list, the initial value for I comes from the first index of A. This is going to be 1. The initial value for j is going to be the last index of A. It's going to be n. And x is the element that I'm looking for. So x is just x. So this triple 1 and x, let me write it here, 1, n, x defines the initial sets of inputs provided to this function. So we are just saying start searching this list A from the first element to the last element. But then we know this is a recursive procedure. Eventually it will have to call itself, and those recursive calls will provide a different value for I and j, hopefully reducing the range between 1 and n and simplifying the problem. So this is my initial input. So let's continue this procedure now. Now we know that in a linear search, we want to start by looking at the first element that we have. If the first element matches, we can return the position. And if the first element does not match, we can recursively call the same function with a smaller list. And in this case, I'm provided a range from I to j in A. So the first element is going to be AI. So I can simply say if x is equals to AI, then return I. So if the value that I'm looking for is equal to the first element in the sequence from I to j, then the first position is the index that I'm looking for. So I just return I. But if this is not true, I cannot return. I need to continue searching. But before continue searching, I want to make sure that the list has not been exhausted. I cannot search anymore if I've searched through the entire list, right? So I need to check that. So I'm going to say else if I is equals to j, then return 0. So I is equals to j means I've looked through entirety of A and I'm just looking from n to n, or from the same index to the same index. So that means that the entire list has finished searching and it was not found. And in case it was not found, we tend to return 0 because the position starts from 1. So any position like 1, 2, 3, 4 should be considered valid, and 0 should be considered as the element was not found. Now in programming languages like JavaScript, 0 is in fact a valid index. Array indices start at 0. So if the element is not found, we tend to return -1. So -1 means element not found, and anything 0 or higher means that the element was found. But in this case, we are assuming A starts from the 1 index. So we are using 0 to mean that the element was not found. And if this is not true and this is not true, I can keep searching, right? Because I didn't find my element and the list is also not completely searched. So that means else I need to just continue searching. And what is the process of continue searching? I'll just return whatever the search function returns. I'll just call it recursively. And see, I did not find the element in I. I want to start searching from I plus 1, the next element. So I want to search from I plus 1 all the way to my last element j. And the item that I'm searching for doesn't change. It's still x. And then this function will call itself and it will check the first item. If it is not found, it will reduce the search space one more time, call it recursively, and this process will go on until the item is found. So this idea of having the list as A1 to AN and also taking the inputs I, j and x, they are going to be exactly the same for linear and binary search as well. So we'll be going through binary search rather quickly. Let's get on to binary search now. I'll just arrange my board this way so you guys can see what we discussed. So we consider the same problem, but now the list is sorted. But the same conventions can be used. We can still call this list A and it ranges from A1 to AN. But this time, instead of starting to look from A1, I want to look directly in the middle and I want to reduce the search space and I want to detect which side my word is, if it is in the left or if it is in the right. And once I find that, I repeat the same process recursively. So let's build that process recursively here. Earlier we called it search. Let's call it binary search this time. I'm just call it bin_search. and we know the arguments are the same. Searching from I to j for an element x in some list A. And I'm not mentioning here, please mention that I, j, x are integers and I and j are between 1 and n. Exactly the same constants that we had in our earlier problem. So in our earlier algorithm, we started by comparing ai with x. So comparing the first element with my search item. But here I want to find the middle of I and j. You see, I is my starting element, j is my ending element, and I want to turn the dictionary somewhere in the middle. So how would I get the middle of indices I and j? I can simply take the average. So I can take I plus j divided by 2. So that means if I'm looking from page 1 to 12, I want to start by turning my dictionary at page number 1 plus 12 divided by 2. And this will be 13 divided by 2, that will be 6.5. But I cannot really turn my dictionary at 6.5. So I'm going to take the floor of this value. Okay. So in order to split the search space into two halves, I'm just going to take the floor of I plus j divided by 2. And if I plus j is even, it will be exactly the half. Otherwise, one element will be more in one side and less in one side. But that doesn't really matter. See, even if you don't turn your dictionary exactly in the middle, you are still dividing the search into two spaces. But dividing in the middle ensures that both spaces are maximum. So let's say you are looking for a word that starts with P and you only turn the first 10 pages of your dictionary. And let's say you find the words starting from B and you are only able to neglect a few words that started with A. When we are sure that either the left or the right half will go away, we might as well keep them equal. Why take risks? Because keeping them equal makes it predictable exactly what size we are reducing. So the main idea of I plus j divided by 2 is of approximately middle. Alright, so let's call this middle position M. We'll find M as I plus j divided by 2 and then we'll take a floor of this value. Now I turned my dictionary in the middle. What do I do next? I see if my word is exactly in the position that I turned. If the word is there, I've already found it. I want to see if the value at the mth position is equal to x. So I'll say that by saying if a of m is equals to x, then I found my word in this position that I was looking for. I can simply return m. But this is very rare to happen on the first try. So what I want to do next is to figure out whether I should be looking into the left or to the right. So let me write this criteria. If x is less than am, so this means that the value that I'm searching for was less than the value that I found. So I was looking for a word with E in the dictionary, but I turned and I found I. So I'm comparing this I with this E. And in this case, E is less than I. This is exactly the same as saying X is less than AM. And in this case, I only want to look at the left half of the dictionary because my word with E cannot happen on the right half. So we'll say if X is less than AM and I is less than M. Because see, since I want to search on the left half now, I want to start at I and end on the middle M. If I wanted to search on the right half, I would start from M and end on J. Okay, so I is on the very left, J is on the very right, M is in the middle. So when I say that X is less than AM, I'm saying that my X is somewhere over here. But if I have finished searching and the word is never found, there will be no left side to look at. Therefore, to ensure that there is still a valid space remaining to search between I and M, I want to make sure that I is less than M. Because if it is not true, it means that I have to look left, but I cannot look left. So my search has to end and I have to return a 0. So I'll say that if X is less than AM, I need to look to the left and I less than M. There is at least a few pages left to look. Then I'll repeat the same process. I'll return binary search. And this time I want to search on the left from I to M. So I'm just going to say I and it's not actually M. So I've already looked at M. So I only need to look up to M minus 1. And I'm searching for the same element X. And all we are saying here is do the same thing with this. Divide this into two halves, find out where X is and keep dividing until you find it. And this if was for the left half and we need to do one for the right half. Else we're going to say if X is greater than AM and J greater than M. I need to look to the right and there is at least some space between M and J to look into the right. And if this is the case, I'll return my binary search again recursively. And where do you think this time? We have already looked at M. So the next form it will be M plus 1. We'll have to look all the way up to the end, J, and looking for X. And finally, if both of these cases do not apply, there is no possibility to keep searching on the left as well as on the right. So I'll just say else, I'll say return 0. The element was not found. So I hope this is clear. Find the middle element. If the middle element is the element that I'm looking for, return M. And else is given in your textbook here. If you want, you can put it here. It's the same thing because we are returning anyway. We could remove all of these else's and the program would still run exactly the same. But maybe don't miss it for formality. But yeah, the core idea is find the middle element. See if the middle element is your item. If it is not, detect if you need to look into the left. If so, look into the left. Otherwise, detect if you need to look into the right. If so, look into the right. And if all of that doesn't apply, say that your element is not found. Alright, moving into the last algorithm for the day. and this is going to be the merge sort algorithm. Okay, so we'll look into the basic ideas of merge sort and then implement an algorithm. So as you know, merge sort is a sorting algorithm. So if I'm given an unsorted list, it gives back a sorted list. So let's say I have a list called 2, 5, anything random, 11, 6 and 1. We know that a sorted list would look like 1, 2, 5, 6, 11. So this is the basic problem of sorting, and there are many algorithms for sorting. They say that an AI recently created a sorting algorithm that is much faster than any that we have. And in general, there are bad sorting algorithms, and most of the bad sorting algorithms are big O of n square complexity. So they need to loop within a loop. In other words, for each element in the item, they need to go through the whole list. For 2, go through the whole list. For the second 5, go through the whole list, right? And those sort of algorithms are big O of n squared. There's a chance computational complexity is not yet covered in your course. So if that is the case, let us just understand that we're looking for better and faster sorting algorithms. And the algorithm that we'll look at today, merge sort, is faster than this lower category of algorithms like selection sort, bubble sort, and other sorting algorithms. So this one we say has a computational complexity of n log n. But let's not spend too much time on this. Let's look at what the algorithm is. So the merge sort works on the principle of merging already sorted lists. So let me demonstrate by putting 2 lists here that are already sorted. So I'll just put 1, 5 and 9 here. I'll put 3, 4 and 11 here maybe. It doesn't need to have equal number of elements. I'm just choosing it randomly. The only requirement is both of these arrays must be sorted. Okay. Now if I want to form one new sorted array containing all of these elements, is there a way to take advantage of the fact that these elements are already sorted? So let us think about what needs to go to the first position of this big array. See, this element needs to be the smallest element in the entire thing. So the smallest one from 1, 5, 9, 3, 4 and 11 should go here. But since these lists are already sorted, I know that the smallest element in this list is the first element 1. And similarly for the second list, I know that the smallest element is 3. So in order to find the smallest element that needs to go here, I do not need to look into all of the elements of the 2 arrays. I only need to compare the first element of the first array with the first element of the second array. So comparing 1 and 3, I know 1 is smaller and should go here. And as soon as I do that, I remove 1 from my original array. And now I have a similar problem of smaller nature. I hope you can also see the nature of recursion at the same time. Now we ask the same question. The first element in here is 5. The first element in here is 3. Which is smaller, 5 or 3? The answer is 3. So we put 3 in our new list and remove it from here. And see, every time we are just looking at the first element in our array with the first element of the second array. So this time I'll just be comparing 5 and 4. 4 will be selected. That will lead me to compare 5 and 11. 5 will get selected. And I hope you can see. Now 9 and 11 get compared. I get 9. And then there's nothing here and 11 here. So this 11 will be selected. Now this is a larger sorted array. So what is the big takeaway here? If I can ensure that 2 lists are already sorted, I can create a larger sorted array by just comparing the first elements of the 2 arrays successively. Now we'll do one merging problem formally because this is also sometimes asked. And then we'll close the lecture by giving the merge sort algorithm, the procedure. So if you want to do this process formally, so if you are asked a question to merge 2 lists, so let's say one list has 2, 3, 5, 6 and the second list has 1 and 4. So if these 2 lists are given to you and you need to do this simulation in your exam, you want to do it by creating a table. Okay, so this table will have 4 columns. We'll say first list and then we'll say second list and then we'll say merged list, and one column will show what comparison we're making. So the first list will contain 2, 3, 5 and 6 and the second list will initially contain 1 and 4. So first you write the comparison and then you write the merged list. So this merged result will be written on the next line. So let me show you what I mean. What comparison will you make at this step? We'll compare the first element 2 with this one. So we'll say our comparison is between 1 and 2. And we know for the next round the smaller element will be removed. So in this case the 2 will remain but the 1 will be removed. So in the next iteration the first list will still contain 2, 3, 5, 6. But the second list will only contain 4. And where did 1 go? 1 went to the merged list. And the comparison that I want to do now is between 2 and 4. And this time 2 will be selected for the merged list. So that means that the first list will have 3, 5 and 6 remaining. The second list will still have the 4. The merged list will now contain the 2. It will be 1, 2. And now you want to see what you want to compare for the next step. So I want to compare the 3 with a 4. 3 and 4. So let me quickly complete the rest because this should be clear enough. And let me stop here. From here, there's no comparison to do. There's no element in the second list. So we'll just take one element and put it in the merged list. So one step 5 will go in and the step 6 will go in. So at this step, I'll have 6 left here, nothing here, and 1, 2, 3, 4, and 5 here. And you should understand this came despite of doing any comparison. I didn't need to do a comparison because there's nothing to compare. And the final step will look like this. So I hope this merging logic and this problem is clear to you. Now we'll quickly build our merge sort algorithm and provide a procedure. Alright, so we just looked into the algorithm that allowed us to merge already sorted lists. So if I had a list that was already sorted, I know how to combine them in order to form a merged list. But our problem here is slightly different. We want to take a list that is not sorted, and from this we need to return a sorted list. So in order to apply this process of merging lists, we'll first divide this list so that each list contains only one element. And we know that a list with just one element is already sorted. So if I have a list with only item 3, this is already sorted. So when I convert my not sorted list with this kind of list with only one element, I can then begin my merging logic. So let me say I'm given a list like 3, 2, 9, 6, and 5. Okay. And the question says that I need to simulate a merge sort on this list. So we'll divide this, taking 3 and 2 on the left side, and we'll take the remaining elements 9, 6, and 5 on the right. If we can make this equal, we do. But in this case, this has an odd number of elements, so we are just choosing 2 and 3. We are still in our process of breaking it down. So let's break this down into 2 lists, one containing 3 and one containing 2. And on this case, we'll need to break oddly again. We'll have 9 on one side and we'll have 6 and 5 on the other end. And I still need to do one break here in order to make them separate, 6 and 5. Now once I've done this, everything is separated into a single element. Now I can begin my process of merging. And the process of merging will be an exact reflection of what happened when you were breaking. See, 3 and 2 got broke. Now these will merge in order to form this set. 6 and 5 broke. These will merge in order to form this one. And this will merge in order to form this one. And that process will repeat until we merge all the way to the top. So let me finish this here. So let me do the task of merging these two. Now as a person writing this, it's really easy. I'll just write 2 and 3. But you should understand that what we are really doing is applying the merge logic from earlier. We are comparing the first element versus the first element. Which is smaller? 2 is smaller. That comes here. And then the second comparison happens between 3 and nothing. And that gives me 3. And in the same way, these two will merge in order to produce 5 and 6 using the merging logic again. And what do you think will happen now? You see, this is a reflection of this one. So 6, 5, and 9 are merging to give this. So this and 9 will merge to produce a new array. And we know it will contain 5, 6, and 9. And you see, now this array is a mirror of this one. And this is a mirror of this one. So these two are merging in order to produce the final array. The same thing will happen here. So these two will merge. And I'll just get my final array. And that array will look like 2, 3, 5, 6, and 9. So if the question gives you 2 lists and asks you to implement the merge sort algorithm, you're just going to draw this tree and maybe use a word or two to explain the merging logic. And there will be another question when they ask you to write the pseudocode itself. So we'll do that here, the algorithm. So let us look into the algorithm that we did here. So we had our initial list. The first thing that we do is to divide the list into 2 sub lists. So this is going to be my first list and this is going to be my second list. Now it is important that I'm able to capture the recursion. What I did from here to here was exactly what I did from here to here, just dividing it into 2 lists. So when I'm writing the algorithm, I want to transition from this list to this list. And this will also be the process of sorting. So the idea is that divide into 2 lists, you sort each list. So 3, 2 is sorted here. 9, 6, 5, the second division is sorted all the way down here. And once both of your lists are sorted, you merge them. Because if you look into this little segment, the same thing happens recursively. We first divide into 2 lists, we sort each of them, they are already sorted, and then we merge them. So no matter in which scale you are looking at this algorithm, the main list will be divided into 2 lists. Eventually those lists will come up sorted. So this 3, 2 came up sorted here, this came up sorted here. And once they come up sorted, we just need to do the merging. So let us give the algorithm now. We'll say this is our procedure, merge sort. And this takes a list of elements from A1 to AN. So we are calling this entire array a list. We are calling the first element A1 and the last element AN. Now we'll say if N is greater than 1, then we want to do something. Because if N is 0 or 1, that means the list is already sorted. So this block will only run if the list has at least 2 elements. And what was the first step? In order to divide the list into 2. To divide the list into 2 equal halves, I want to see where roughly the middle is. Same as our previous problem of binary search. So I'm going to find that middle. And this is going to be the floor of n by 2. Now once I find this middle element, I can separate my list into two sublists. So I'm going to say that my left sublist is going to contain the elements of A from 1 to this M. So the list L1 will contain the elements A1, A2 all the way up to AM. And the second list L2 will call all the elements after AM. So it will be AM plus 1 all the way up to AN. Now what do I need to do next? I need to sort this list, and that happens recursively using the same algorithm. So I'm going to say sorted list 1 is equals to merge sort L1. I'm going to say sorted list 2 is equals to merge sort L2, and I'm going to initialize my final sorted list L as merge. I'll tell you what merge is. That's the same process that we did here in order to merge the already sorted lists, and I want to merge SL1 and SL2. So looking at it again, find the middle element, divide the list, everything from start to the middle, everything from middle to the right, and then you sort those individual lists, and then you merge those sorted lists. Divide, sort, and then merge. Now I'll make a quick remark. In your textbook, this merge sort L1 is just written here. So I'm just introducing these variables to make it more readable. So from this line L1 and L2, you could directly write L is equals to merge sort L1, comma merge sort L2. Really basic if you have some idea in programming or even algebra and substitutions. It's just a basic concept. So just mentioning in case the discrepancy doesn't confuse you. And finally, we already know how a recursive algorithm works. So this list will be divided into this list and this list. And in order to sort this list, I'm calling the same algorithm again. So this algorithm will be called on 3, 2. And that means it will again find the middle and divide it into 3 and 2. This happening. And eventually when we have only one item in the array, n is greater than 1 will not execute. That means the same list L will be returned. So I think we can remove the ambiguity by writing return L. And to be even more clear, this return L is outside the scope of the if statement. So if you want to consider this in a block, it starts here and ends when this list is calculated. That means the list already has only one element. The whole if thing does not execute, and simply return L will execute. That means the same list will be returned. And by doing that, we are saying that a list containing only one element is already sorted. Alright, so that is all the discussion we'll have for today's video. So thank you guys so much for watching. See you guys on the next one. Have a good day and bye.